Hey everybody, thank you so much for coming. I'm Jonathan Frankel. I'm Chief AI Scientist here at Databricks.
Hi everyone, my name is Avi. Sorry about that. I'm on the NLP team, and I recently led development of DBRX, our open source model we're talking about today.
Yes, so today's session, this is going to be a longer session, but the goal is to talk to you about how we built DBRX, everything that went into that, why we did it, how we did it, and how that technology is now available to you. Avi was the architect who oversaw the entire project. You'll be hearing from him in the second half. I'll give some framing material in the beginning. I hope everybody's ready for a nice long session. We're going to have a good time. Awesome. So first of all, let's talk a little bit about DBRX. And really, first, I want to give a pronunciation update. It is no longer pronounced DBRX. It is now DBRX. We decided a dinosaur mascot was an appropriate thing here. So just to make sure everybody's on the same page as we discuss it. And really, the best place to start is, what do we even do? Avi and I, both work on the Mosaic research team here at Databricks. We're veterans from Mosaic ML, and we joined Databricks almost exactly a year ago. And our mission within Databricks is pretty simple. We want to help everybody build and serve custom AI models. And you can only have custom AI models if you're using your own unique data. And we think there's value to having your own unique data incorporated into models. We're not big fans of a one-size-fits-all approach. We're not big believers that one giant model is going to solve every single problem or solve it well. We think customization and unique enterprise data is going to be at the heart of how AI gets deployed in practice. And the goal is really, you need this to achieve the highest quality in your domain, and you need to do it as efficiently and cost-effectively as possible. I think a thing you're going to keep seeing throughout this presentation that is core to our whole philosophy is it's about ROI. If I told you that you could have a GPT-4 quality model on your data and it cost you $10 billion, you probably wouldn't do it. If I told you it cost $10, you'd probably do it yesterday. ROI dictates everything about how we invest in Gen AI, especially because it is really expensive to build and serve these systems. So I just want to make sure you understand our philosophy and why we're here. And we can take you everywhere, from API calls on the GPT-4 API or calling Llama 3 to full-on pre-training your own DBRX class and above models. I still, as far as I understand, believe that is unique in the entire industry. There's nowhere else that can take you on this full journey to pre-training your own models, just us here at Databricks. So what is DBRX? What are we doing here? What is this model? Just the fact sheet. It is an open LLM built entirely here at Databricks. It's available on Hugging Face. You can go and get it today. 132 billion parameters, but thanks to its mixture of expert architecture, behaves more like a 36 billion parameter model in practice. And again, we'll say more about that in a little bit. It is a leading open model on popular benchmarks. It was, at the time of release, the best open source model in the world. We lasted, I think, 3 or 4 weeks, which is actually pretty darn good in the open source world these days. That's a lifetime. So really pleased with that. And Llama 3 came out and changed the game again. I'm really proud that we're still holding our own against Llama 3 with about 1/50th of the budget from my best guesses. So very proud of that. And I'll say one more thing about this, which is, people like to make comparisons between open source models. Databricks does not make any extra money if you use DBRX instead of Llama 3 or any other open source model, Mistral, what have you. It's just another open source model. And if you choose to use it, it will win on its own merits. There's no reason that you should use this over any other model unless it's better for your use case. That's true on Databricks, and that's true everywhere. So I just want to make sure we're clear on that. So why did we do this? It's a big investment. It's a pain in the neck to build one of these models. It feels like a lot of fun in hindsight, but I don't know if it felt like a lot of fun for the 9 months that we were working on this project. It wasn't to build the world's best model. It was a really nice side effect that it was a really good model, but we're not here to play the one-upsmanship game. It's really a bunch of things. One is that you can come and pre-train your own models from scratch on Databricks. And we always want to stay a couple steps ahead of where our customers will be. This is a pretty big, beefy model, and we're hoping people will grow into that over the next year, but we wanted to make sure we were ahead. This is a big upgrade to our training stack. Our last iteration of our training stack were the MPT models, which we created about a year ago now. And this is a big update. I'll show you some numbers, but in many ways, I think you can say this is about 4x more efficient to build the DBRX class model than to build an MPT class model, and probably about 2x more efficient than a Llama 2 class model. We're really proud of that. Our goal is to reduce cost and improve ROI, and this is a huge ROI improvement for anyone who's trying to train their own model here at Databricks. The other piece was we wanted to stress test and improve Databricks for Gen AI. Databricks is an amazing platform. It had never really been tested at this scale across the board. Everything from, how do we do data ingestion of big Gen AI data sets? How does Spark function here? Can the Mosaic stack actually train this model effectively? How is our inference solution? How is our monitoring and experiment tracking? And we pushed the limits on all of our technology, and it got a lot better for these kinds of use cases because we really battle tested it. I'm really proud of our peers in the product teams who, we broke things, they fixed them and made them a lot better and a lot nicer to use in these particular situations. And now that means everybody in this room can benefit from that. And that was one of the big goals for the project. And you can see some of the tools here across the board, thinking of, Lilac AI for exploring data, Apache Spark for notebooks. Spark is the Databricks mainstay. And as soon as we moved to Spark, our data team velocity improved dramatically. Unity Catalog, we used it for governance of all of our data. We used the Mosaic AI pre-training product, and MLflow and Lakeview for monitoring our experiments. Lilac AI was not a Databricks product at the time that we trained DBRX. It is now a Databricks product. We acquired them, on the basis of how helpful they were during the DBRX process. We thought it was an important part of the platform that we needed to have. And this talk is really about how to build custom DBRX class models. That's going to be the focus today. It's really fun. I will say it is not for the faint of heart. If anyone here comes to me and says, I would like to train a DBRX class model tomorrow, my answer to you by default will be no, don't do it. I'll mention in a moment kind of a little bit more about my philosophy there, but you have to work your way up. It takes a certain level of data maturity, evaluation maturity, and business need. It's an expensive, intense proposition. We have lots of folks who do it. They all have a good reason. And I'm happy to chat afterward if you have a good reason and we can work our way there. I'll still insist that you work your way up from fine-tuning and continued pre-training to doing full-on pre-training because it's the kind of thing where you take one swing at it and you have to hit it on the first try. So I like to start the formal part of this talk with friendly advice. It'll sound like vague platitudes now, and by the time we're done with our 90 minutes together, I hope that this resonates as deeply for you as it does for me every time I look at it, having felt the pain personally that led to every single bit of this friendly advice. For starters, start small and work your way up. It sounds trite, it sounds kind of silly, it sounds obvious. Please do it. I think every good use case should start with trying to prompt GPT-4 or Llama 3 70B and seeing how it goes, and trying to do RAG, and working your way up from there through fine-tuning, continued pre-training, all sorts of other stuff to full-on pre-training. And hopefully somewhere along the way, you find a solution, and full-on pre-training is not necessary. But the nice thing is that each of these smaller undertakings is basically negligible in terms of cost compared to the next thing up the ladder. So you don't really have an excuse to skip a step. You should follow every step because it costs you almost nothing in terms of time and money compared to what comes next. The next thing, and this is kind of, I say this as an academic, don't trust what you read in the literature, test everything for yourself. I think this is a very hard-won lesson for us, and this is not meant to denigrate the academic literature. And I say this as an academic, I have PhD students, I have a PhD. It's really about the fact that in industry, we just have many more resources, and we can test these things at scale and with levels of rigor that are just unavailable to folks in academia. And sometimes ideas that work really well at small scales do not scale up very effectively. There are quite a few papers that have been very popular in the past year that we have not been able to reproduce internally. I don't like to call that out publicly. They're typically written by PhD students. These are scientists in training, and that's not the right way to handle that. But we certainly learned some lessons the hard way about trying to redo things before we actually use them in practice, just to make sure they really do generalize. By that same token, don't trust your intuition, received wisdom, a rumor you heard on Twitter, your friend of a friend at OpenAI. Test everything for yourself. It's really, really important. My intuition has misled me so many times over the years. Somehow I'm still in this job, despite the fact that I'm wrong a lot more than I'm right on intuition. I remember GPT-2 coming out and going like, why would someone want to just create fake language? Who cares about that? And it's not very good either. And here we are. I said the same thing about GPT-3 for the record. So, take my intuition with a grain of salt. Data is king. Evidence is king. Science is king. The last part, and I hope this will also take on resonance, do the math. Abhi and I are both going to do some math during this talk. It's not hard math. There's no calculus involved. We have AutoGrad for doing calculus. You don't need to worry about that. but you can do the math and reason very well about the properties of these systems, how much they're going to cost and how long they're going to take to train and how to build them well, and we'll do some of that math. The last piece here is, usually I would give this talk to an academic audience. This is a friendly audience of folks who care enough about Databricks that they bothered to come to Data and AI Summit and are in this room. If you're a customer, we're here for you. We are your research team. Our goal as a team is to keep up with the literature, figure out what works and what doesn't work, and pass that knowledge on to you through our products, through our papers, and through conversations. So we're here to be your research team and support you in this endeavor. We can help you do the math. We have your back here. That's really the biggest takeaway. Everything that you see here, we have suffered through so that we can give you good advice. Okay, roadmap for the talk, very briefly. Number one, we got to define success. We have to always start with evaluation. Abhi loves to say and will say, you need to have a measuring stick. We found that our team is very, very good at, on whatever measuring stick, making the number go up. Making sure you have the right measuring stick and you're making the right number go up is incredibly important. Then you have to understand your budget, and we will talk about model and data set size and what makes sense there. There's a lot to fill in terms of which model and which data, and then you got to go and train the thing. And there's a lot of work to do in scaling and infrastructure. If you're a Databricks customer, we've taken care of all of that for you. We've trained large-scale, hundreds of billions of parameter models on thousands of GPUs and built that infrastructure out and codified it into libraries and products so that you can just go and take it for a spin. So I like to start at the end with evaluation. You cannot make progress until you know what success looks like. What you really need, just kind of from a philosophy perspective, I think of this as three things. Number one is you need something cheap and automatic, something that is almost like a unit test. Every time you write a new pull request, push the run unit test and see if you pass the tests. Something that is that easy and that quick. You need something somewhat involved and more realistic, something that starts to push the limits on looking like the actual task you're doing. The evaluation may not be perfect, it may be a little bit subjective, but it gives you more of a sense for how you're doing on real benchmarks. Then you need something close to the real world. This can be slow and expensive, but you still need to know when you're doing the right thing. So I'll go through kind of what we recommend and what we did. For DBRX, we used this thing called the Mosaic Gauntlet. I'll actually, I'll show it to you in a moment. But this is really your inner development loop. It typically has right and wrong answers. These are benchmarks like MMLU is a very popular one. A lot of knowledge-based questions. These aren't going to test your model on actual generative tasks or anything subjective, but they are going to give you a sense for whether you're moving in the right direction, your model is getting better in certain categories. We do have the Mosaic Gauntlet for this. It's a collection of now 39 public benchmarks split across 6 categories. This is a blog post we put out, about a month or two ago on updating this. We've done a really painstaking job trying to remove benchmarks that don't have signal or that are completely saturated because they're not very useful. Now, when you get to something more involved and more realistic, you need to evaluate the generative behavior of the model. It's not enough to just get a multiple choice question answer. This likely uses LLM as a judge. I have my qualms about using LLM as a judge, but at the same time, I can't think of anything better. And that's true for a lot of deep learning stuff right now. I don't like a lot of what we do, but if I knew something better, we'd be doing it. And that's the world we live in today. For DBRX, we were using things like MTBench, IFEval, the Chatbot Arena hard data set. These are things, they are subjective. I don't expect perfect scores and I don't expect perfect accuracy in terms of the model evaluating things, but they give us signal on things that are more subjective and more generative. Then you need something close to the real world, ideally real human evaluation. Sometimes you have to go and procure that data from a third party to have some humans go and look at it. Sometimes you can do that in-house. Although if you've never done actual human annotation in-house yourself before, I recommend going and trying to do pairwise comparisons of outputs of models just so you understand how painful it is. We made our team do this once just for empathy's sake, and I think people started quitting after about 20 minutes. It's a lot more painful than you think to read essays on historical events you don't know about and try to look for the factuality, or check long Python programs to see if they're correct. It sounds a lot easier in theory than it is in practice. So for DBRX, we're using human annotation and a lot of customer feedback. But the nice thing is if you're in a real enterprise setting and you've got a process where this model is slotting into, slot it in and do some A/B testing. Have humans review the outputs of the model in your existing process. There's a lot of room to just stick this in, and you have all this stuff in-house in a lot of cases. For image models, human preferences in a real product matter. I think it's important to just say about evaluation, you gotta read your eval sets. You gotta look at them closely. I love the benchmark HelloSwag. It's a great common sense reasoning benchmark. I like to point it out just because people use it, I think, blindly and take it as, oh, this must be a good benchmark because I saw it on a bunch of papers, and maybe it's in the OpenLLM leaderboard. This is a question from HelloSwag, and I think it's instructive to look at it. Multiple choice question. A woman is outside with a bucket and a dog. The dog is running around trying to avoid the bath. She does which of the following, which makes the most sense? She rinses off the bucket with soap and blow dries the dog's head. She uses a hose to keep it from getting soapy. She gets the dog wet, then it runs away again, or gets into a bathtub with the dog. These are really weird questions that were not designed for evaluating LLMs. This came out a lot before that. And yet this is something I think a lot of people rely on without looking at it very carefully. It's important to know your evals and know what's going on. There's been a lot of work on this. Are we done with MMLU? We identify errors in MMLU and find that subsets are riddled with errors. This is last week. This is from an internal Slack conversation. So many errors on BirdBench, which is a popular text-to-SQL benchmark, are in fact the model making a reasonable guess at the user's unclear query or providing helpful context. We estimate that somewhere around 70% of GPT-4's quote-unquote mistakes on BirdBench should be marked as correct. This is how people get to claim their models are better than GPT-4 at things without being super careful. And it's great to claim that. Our friends at Inflection evaluated MTBench and found, and this is on an 80-question benchmark if I remember right, nearly 25% of the examples in reasoning, math, and coding categories had incorrect reference solutions. This isn't to say these evaluations are bad or people are doing a bad job. It's just hard. And you shouldn't just look at these numbers blindly. You should go and understand what they're measuring and know what signal you're getting from these benchmarks. My deepest, darkest fear is this kind of conversation. A customer comes to me, one of you, and says, we just spent a huge amount of money training an LLM with you. Is it good? That is my deepest fear. You should know ideally how good it's going to be beforehand. We should have thought about scaling laws and figured out what it's going to look like on your benchmarks. We should easily be able to verify afterward. You shouldn't need to ask me. So I'm spending a lot of time on evaluation for something that ostensibly has nothing to do with DBRX. These are some hard-won lessons for us, and I think it's important to take them away. Okay, model and data size. You gotta understand your budget constraints and plan accordingly. I'm gonna go through this in 3 iterations where we get increasingly sophisticated about how we think about cost. Number 1 is let's just think about training compute. You have a budget of some amount of money. I'm gonna give you $1,000 or $100 million. Take your pick. You'll pick the 100 million, but that's another can of worms. Train the best model. The cost of training is approximately, and this is an approximation, so people who know better, you can quibble with me later, the model size times the amount of data, plus or minus. One extreme, if I gave you this budget, is like train a gigantic model. Train a 1 trillion token model on 100, or 1 trillion parameter model on 100 tokens. That's gonna be terrible. It's only seen 100 tokens of text. The alternative, train a 100 parameter model on 1 trillion tokens of text. Also probably gonna be pretty terrible because it's only got 100 parameters. There's probably some sweet spot in between where you've spent your budget optimally. We've kind of sandwiched it on either end. Where's the middle? And knowing where that is really important. This is where there's a famous paper that has become known as the chinchilla paper because they train the chinchilla models for this. Great paper from DeepMind, kind of ahead of its time in a lot of ways. And here's basically what they found. If you're trying to spend your budget optimally, figure out how to spend your budget such that the number of tokens of data is about 20 times the number of parameters. This is still a rule that you'll see shake out if you start to do scaling law work today, plus or minus. 20 seems to be the golden rule. When I was training to be a real engineer instead of a computer scientist, they always told me there were certain numbers you just needed to know, conversion factors and things like that. This is one of those numbers, the number 20. So it's worth keeping that in mind. This is one of my favorite graphs in machine learning. This is a graph from that paper. The x-axis is the size of the model. The y-axis is the training loss. Lower is better on this. And each of these curves is for a fixed compute budget, training a bunch of different models at different sizes. And the bigger the model, that means you're training on less data. You're still spending that same budget, just you're varying how big the model is versus how much data. Notice that each of these curves has a nice minimum. That's the sweet spot. That's the optimal size. That's about 20x. I love this graph. Okay, now that's not enough. Let's start to think about lifecycle compute cost. Eventually, you will need to serve one of these models. So now we're trying to train the best model and perform inference and spend our budget wisely. It's probably worth training a smaller than optimal model to reduce your inference cost if you think your inference cost is going to be meaningful. As a nice side effect, big models are just a little more unwieldy to train. They kind of push the limits of checkpointing. They push the limits of how much you can fit in GPU memory. They sometimes optimize a little bit weirder than smaller models. There are a lot of good reasons to train something smaller than optimal and decide you're not going to be optimal at training time because you're going to be optimal for other reasons, to save you pain or at inference time. So this is really what Llama did that was so interesting. They said, to hell with chinchilla in some sense. Let's train, for a lot more tokens than chinchilla suggests. For any given budget, we will get a worse model than we could have otherwise. But we're thinking about the life cycle. This is going to be easier to serve. This is going to be easier to train. And in fact, this is part of why I think Llama got so popular. It was easy to put on gaming GPUs at home. There were models like Bloom that came before this that were 175 billion parameter models, or models like OPT that were in that space. You just can't put that on a gaming GPU. I think this is really why Llama caught fire. And I'm putting some TPRs, token to parameter ratio. So Chinchilla's 20x. These are for some of the Llama models. Llama 2 7B is about 285x, so more than an order of magnitude. Llama 3 8B is almost 2000x. They chose to be really suboptimal. If you were to have spent that compute in a chinchilla optimal way, you would have gotten a much better model. But it's really cool that you have a model that good in an 8 billion parameter size. That's pretty incredible. They made that choice, and I think it's a reasonable choice. So when you're pre-training, you have to make this trade-off. DBRX was making this trade-off, where we did not do chinchilla optimal. We actually went a little bit further along. I believe it was an 80x token to parameter ratio, because we wanted to make sure it was easy to serve. Okay, now we've got compute and data cost. This makes things even more fun. Between you and me, I would estimate that the Llama 3 training costs for the model so far, if you look holistically, I would guess they spent about 90% of their budget on human data annotation and about 10% on compute. Avi, you're welcome to tell me I'm wrong about this, but that's my best guess based on doing the math. And that should tell you something about where the world is moving. So the way that I look at training personally, and this is kind of how we looked at DBRX, was in 4 phases, and I'll go through each of them. This is, for those who were at my talk earlier this morning, I gave a much simplified version of this diagram and promised you something more fun. This is the more fun part. So it's in 4 phases. Pre-training, which in the DBRX case, it was 12 trillion tokens. When I used to put this slide up prior to releasing, or prior to Llama 3 coming out, people looked at me and were like, nah, 2 trillion. What are you talking about, 10 trillion? We're in the tens of trillions, firmly in the tens of trillions at this point, and general data. Curriculum learning is kind of interesting. I'll tell you about that in a moment. But it's closer to 1 trillion tokens. You can think of this as the tail end of pre-training, where you get a little pickier about which data you train on. Typically higher quality, you upsample the good stuff. Fine-tuning, if you're doing instruction fine-tuning, is typically 10,000 to 100,000 instructions, somewhere in that ballpark, I would guess. And then RLHF could be 10,000 to 100,000 preferences. Again, these are orders of magnitude. We'll look at some examples in the real world in a moment and see what people have done. So for pre-training, this first phase. There's a lot of cool data out there. This is not an endorsement of any one of these data sets, but there's a lot of neat stuff that's floating around in the open source community. People have done a really good job putting cool stuff out there. I personally think the StarCoder data set was like a big achievement for putting out open source data sets. I even look at the pile. It's not a data set that most folks recommend training on today just for quality purposes. It was a visionary that they put this data together in 2020, years before anybody was really thinking about this in a meaningful way. But your data is part of this. Notice that your data is kind of off to the side and is not that huge because not everyone has 10 trillion tokens worth of data internally. That's a lot of data. That's the size of the web many times over. But mixing your data in will make a huge impact in the same way that mixing Wikipedia in makes a huge impact on the quality of the model for factual purposes. For curriculum learning, this is a fun little animation. You upsample the good stuff. In this case, I picked some random stuff like Wikipedia I think is pretty good, StarCoder seems pretty good, and start to downsample some of the other stuff. What we found empirically, and we put out a paper on this, I believe on Friday, that if you take that last, say, 10 to 30% of pre-training and you change your data mix to upsample some of the stuff that's higher quality, you'll get a dramatically improved model. Much better than if you just were to keep pre-training on the same data. Now, the nice thing is that although it's really expensive to pre-train the model multiple times, you can experiment a lot with curriculum learning, especially at smaller scales, and try out a lot of different data mixes until you find something that really works for your evaluations. But this relies on you having good evaluations, so keep that in mind. Phase 3, instruction fine-tuning or fine-tuning in general, about 10K to 100K instructions. This is where your data really starts to shine. In curriculum learning, you upsample it more. Here, this is where it's going to shine, especially if you have any kind of process that's just generating good examples. If you've got a process where humans are summarizing documents or things like that, this is where that data becomes invaluable. Or you can go to human annotation and work with a partner. I would say the order of magnitude is in the tens to hundreds of dollars per example, just to set expectations. It varies a lot depending on what you're asking for. I'm going to pull out a quote from the Llama 2 paper because they were actually very candid about this. We found that SFT, supervised fine-tuning, it's another word for instruction fine-tuning, annotations in the order of tens of thousands was enough to achieve a high-quality result. We stopped annotating SFT after collecting a total of, and they're oddly specific here, 27,540 annotations. And of course, note that they didn't use any meta-user data. But they said a really interesting thing that I think it's worth picking up on. Surprisingly, we found that the outputs sampled from the resulting model were often competitive with data handwritten by human annotators, suggesting we could reprioritize and devote more annotation effort to preference-based annotation for RLHF. I would say that this is the Llama folks saying that on Llama 2, they used a lot of synthetically generated data, which is really interesting. Synthetic data has become a bit more of a popular topic. Our experience is use with caution. There's a right way to do this and a wrong way to do this, and it can get a little risky. But it's kind of interesting that they just mentioned this. And this was probably a year ago or more when they trained it. So for fine-tuning, I'll throw in synthetic data here. It's worth keeping in mind. The last part is RLHF. For those who aren't familiar, I'm not going to dwell on this, but it really is kind of human preferences to help capture that, like, I know it when I see it aspect of models that are hard to put in a single supervised example. People decide which example they like more, and you train your model to output things that humans are more likely to prefer. I would say in the order of 10 to 100K preferences might be typical at this point. I always pause here because a lot of people say, well, I don't have any of that. Yeah, you probably do. If there's any data process you have that's interacting with users, those users are probably interacting with that process and producing preferences. And integrating a model into that process can be really powerful. Something worth chatting about, with folks at Databricks, because we tend to be pretty good at spotting these opportunities. But I found very few folks we've worked with where they've needed to go out and procure a ton of their own RLHF data. They typically have a data generating process internally where properly instrumented, they're getting those preferences already. Human annotation, I would say in the order of $5 to $20, somewhere in that ballpark, so a little lower per preference. Here's what Meta said for Llama 2 7B, or Llama 2 in general, and they did put a lot of work into safety. In total, we collected 14 batches of human preference data on a weekly basis consisting of over 1 million binary model generation comparisons. If you wanted to, based on my ballpark numbers, you could do the math for data here. Then you can look at what Meta said about Llama 3 and how much data they collected and do the math there and kind of roughly back of the envelope get to the number I said before, my guess that perhaps 90% of their budget actually went to data annotation rather than compute. Okay, so which data? You really are what you train on. So this is an exercise I love to do. I'm actually going to treat this like a class for a moment. Take a moment, grab your phone, grab a pen and paper, whatever you prefer. I would like a 1 trillion token pre-training data set. Here are the resources I'm giving you. You can look at this, some web data, some code data, Wikipedia, different languages, some science papers, those are pretty good, some literature. So that's really, that's the most important part. If I told you I wanted a coding model, you should make very different choices than if I told you I wanted a model that was really, really good at languages spoken in East Asia. Really important to keep in mind. Anybody have a thought as to a data mix they might throw at this if I told you just like ChatGPT? Give me something like ChatGPT. Anybody want to be bold? I can really go into professor mode and cold call somebody. Now, so let's look at what some other people did. This is the original Llama data set. It's the only one they've ever specified. I will, if you're looking for a great pre-training data set, I would say this is not a modern standard that you should live by. But it is kind of interesting. Those first two data sets are web crawls. It's about 82% of their overall data set. GitHub was only 4.5%, which is on the low end. In papers that talk about this, you typically see 20 to 30% today. Wikipedia, 4.5%, some books. They took papers from archives, Stack Exchange, this, a lot of the kind of stuff that, this looks a lot like my reading diet for the most part, if I really think about it. Notice in the epics, they tried to avoid repeating data too much. The only data sets they repeated more than once really were Wikipedia and books. Again, I won't say this is the gold standard at this point in time. A lot's changed in the past year or two, but it is interesting to see something. So I'm going to talk about the value of better data. I'm going to show you, this is MPT-7B. This is a model we trained about a year ago. It was trained on 1 trillion tokens, so 1,000 billion tokens. We made the data set probably last April. And on our gauntlet, and this is our internal benchmark that we use to look at models. It's, you can go and take a look at it online and see if you like it or not, but it's a metric, 30.9%. We then retrained an MPT-7B using the DBRX data set. It got 39%. Huge improvement. An 8.1 percentage point improvement. Those don't come easy with a better data set. Then we tried this cool experiment where we tried training that same architecture on the DBRX data, but with half the number of tokens, and it still did better. The way to think about this, if you really want to, with a better data set, we get a better model with half as much data. Or every token of our new data set was worth twice as much as a token of our old data set. This is the power of data, and I don't think you should lose sight of that. Okay, so there are tons of key questions about data. How should you mix it? Should you focus on freshness or repetition, quality versus quantity? Should you deduplicate your data? These are all great things to discuss in a context-specific way. The main lessons I would give you here is, it's a little in the middle for all of these things. Too much deduplication is a problem, too little, and you will end up with a lot of repetition. For mixing the data, we actually have found typically that just uniformly sampling over all of your data sets works quite well, with certain caveats, and that it is a mix of quality and quantity that matters. You don't want to just look at Wikipedia 500 times. You do want to see a variety of data, even if it is lower quality in your estimation, and what looks low quality to you may not be low quality to an LLM. Don't assume that just because it's your reading diet means an LLM will do well based on it. Run experiments and let science be your guide. So how to run those experiments, start small and work your way up. And what that means in practice is start with small models and see how your metrics improve as you scale. Now, there are risks here. Some of your metrics may not even have signal until you reach a certain scale. This is one mistake I see a lot in the literature. If you wanted to get signal on a popular coding benchmark called human eval, you literally need to train Llama 2 7B. You need to train a 7 billion parameter model on 2 trillion tokens. You train anything smaller than that, you're in the noise. And there are papers out there that train things smaller than that and look at this benchmark, and they're comparing noise to noise. It's a big risk factor. So here's how I really recommend it. Get a running start. This is where curriculum learning shines. Do something reasonable during phase 1, during pre-training, and do your extensive experimentation during curriculum learning at smaller scales. Try out lots of different data sets, lots of different upsampling, and see what really helps the model during that last 10 to 30% of training when you can afford to really iterate and where you've already got a pretty good model. Take Llama 2 7B and build on that and see what data makes the most sense. You're not going to get it perfect. If you take a look at the Gemini 1.5 paper, they mention this. This is basically their strategy because you're not going to train a Gemini 1.5 Pro or Ultra more than once if you're Google. And as a customer, we have intermediate checkpoints for a lot of these models. So these are around. Okay, last thing I'll say about data is data logistics. You have a huge amount of data. Where do you put it? How do you get it to your training cluster? How do you shuffle it? How do you ensure determinism? I'll give you an easy answer. We encountered all these problems and we just built a library to do it. We don't make any money off of this. This is just free and open source, but you're welcome to go use it. This is what we use every day to train. We keep all our data in our cloud object stores. We stream it to wherever we need to stream it to. From an egress cost perspective for text data, the compute intensivity per bit is so high when you're training LLMs on text data that the egress costs barely register relative to the GPU costs. So, I wouldn't worry about that too much. It's a great way to eliminate data gravity. And, it's a tool that we use every day. You're welcome to enjoy it as well. Okay, which model? Avi, I believe it's your turn.
Thanks. All right, testing the mic. Is it working for everyone? All right, great. So I'll be talking a little bit about the modeling decisions we took when building DBRX, as well as some of the challenges we had when actually scaling up to a 100 billion plus parameter model on thousands of GPUs. And if at any point you see during this part of the presentation, like, oh my gosh, that's so difficult, there's no way I'm gonna be able to do it, don't worry. The reason we did this at all was kind of as a proof point, and we built a product that basically eliminates all the complexities for you. So this will be kind of a deep dive, but it doesn't mean you have to repeat all the same trials we went through. Oh yeah, and of course the model we're training will be a transformer, but we'll get into some interesting details. So when it comes to training or pre-training models from scratch with Databricks, our advice is to basically follow the beaten path, take recipes that we've tested over and over or other people have, and basically at most add small tweaks to them. So we're going to train a transformer. We're going to use the same loss functions that people normally do, which means that we're going to train on next token prediction. We're going to use full quadratic attention. You may have seen that there are some people proposing local attention variants or sliding window attention. We prefer to actually just use the most vanilla version, but just optimize the performance of that. And then we're going to use the same kind of scaling rules that Jonathan was talking about, right? So how to basically proportion the amount of data and parameters. And I think when it comes to the choices we made over the original MPT series, a few small adjustments we had were kind of the optimizer we use. as well as kind of the embedding. So rather than use alibi positional embeddings, we now switch to rotary positional embeddings, just for the benefits of inference support and basically matching what other people had done. Now, there are some improvements, some major improvements over our training stack from just a year ago. Basically FP8 and mixture of experts. One of those is a change to the precision we use, like basically the math precision that we use to matrix multiplies. And this is important because newer GPUs actually have, basically are able to do lower precision math faster than higher precision math. You basically get 2x improvements when you go from 32-bit to 16-bit to 8-bit math. And so being able to optimize with 8-bit weights and activations basically lets you use this hardware gain. Now, MOE, or mixture of experts, is a model architecture change. You may have heard that Gemini, I think 1.5 Pro was a mixture of experts model, whereas the previous models were dense models or vanilla transformers. And what this gives you is basically you get an efficiency boost both at training time and inference time. And I'll explain how that works. So let's go into FP8 first, actually. I want to just give like a brief overview. Although I mentioned these new hardware GPUs like Hopper H100s, although they see like theoretically a 2x gain, what we find in practice, and we have a blog post publicly as well, is that when you train with FP8, you get nearly 1.5x improvement. So that basically means that your budget can go 1.5x farther. Train a bigger model, train on more tokens, get a higher quality result. And you can see that even when we train the exact same model recipe with FP8 versus bfloat16, the gauntlet eval score that we got is pretty much the same. In fact, we actually saw slightly better results with FP8, which is something we were surprised by and we're actually investigating more now. But it seems to be that whatever the numerical risks there were with FP8, basically with the recipes we have now, it's not a problem. Now, mixture of experts, the architecture change, we're going to dig in step by step through here. Let me just put these up. So basically, you can imagine that the quality of your model trends with the amount of compute you throw at it, right? So bigger models trained on more data are better. But the problem is when you serve these models, they get slower and slower, and you need more and more GPUs to host them. So they're more expensive to serve. So the basic idea of mixture of experts models is, can we have a bigger model get the higher quality boost, but only activate a small fraction of it for every single input? And so you basically are able to increase the capacity of your model without necessarily increasing the serving cost per token. And that's what mixture of experts are. You end up getting this thing where you have the quality of a bigger model, but you get the speed and throughput per dollar of a smaller one. So what does this actually look like in practice? Let's kind of zoom in on one block of a transformer. So all the models we trained today are transformers, and here just looking at just one block. We feed the transformer tokens, which are basically little chunks of a sentence, and they go through these different layers. You go through the self-attention layer, you do some operations, you go through the feed-for layer, the FFN layer, and traditionally you have one set of weights, one set of learnable parameters for each of these components. And every token that goes through goes to the exact same single set of weights. That's vanilla transformers. Now what we're going to do to try and achieve this thing where we get the bigger model but only activate a part of it is we're going to replicate the FFN layer. So we're going to create multiple copies of it, and so we'll create an expert's numbers of copies. If you look at some popular MOE models out there like Mixtral, they may have 8 experts and activate 2 of them. DBRX has 16 experts, so 16 copies of that feed-for layer. And what we're going to do is we're going to let each of those individual copies get learned independently. And for each individual token, we'll route it to the experts that make the most sense. Okay? We'll learn basically a routing function, and we'll only send it to a subset. So if you think about some of these ratios I mentioned, like 8 experts choose 2, or 16 experts choose 4, we're basically only activating 25% of the parameters on every single token. So now let's kind of zoom in one step further. And what does this actually look like here? Here, this is an example of an MOE with n experts equals 4, top K1. And you can see that for the 2 different tokens we're feeding, token A and token B, they both go through the same self-attention weights. But they get to this routing function, which basically looks at that token and determines, okay, the experts that are best suited to process you are expert 2 or expert 1 or a combination thereof. And you can see that they actually go through different parts of the network before they get out the other side. And this is basically how we're able to achieve this thing where the actual network has gotten a lot bigger, like almost 4 times bigger than before, but it doesn't mean the amount of work is 4x. The amount of work is just the same as if it had been a vanilla transformer. So that's how MOEs work. And there's a lot of details in terms of basically making sure that these routing functions are balanced, making sure we don't accidentally over time, send everything to expert 1 or everything to expert 4. And there's a lot of tweaks you have to do to make sure you can actually train these efficiently as well. And one of the biggest challenges we faced with MOEs, which we hadn't faced with dense models, was that when you distribute your work across these huge GPUs, you want to make sure you don't face straggler problems, right? It would be really bad if on each step, one of the experts had a little bit more work to do than everyone else, and so it slowed down the whole step. And so MOEs come with really great theoretical and empirical benefits of training inference time, but there's systems challenges that it comes with as well. And that's sort of what our stack has been optimized for. So, let's look into those kind of benefits actually of mixture of experts models. So this is similar to some of the slides Jonathan showed. If we look at a very classic popular model from last year, Llama 2 13B, and we look at both its eval gauntlet score and the amount of flops that are spent on it, we can basically train a DBRX model. And this is one of the kind of gating runs that we did before we trained the full DBRX, where we can basically achieve the same quality, or actually slightly higher evaluation quality, with almost half of the flops, right? So with half of the compute, we're still able to achieve the same eval score. And not only that, because this is a mixture of experts model and we tweaked the parameters the right way, the amount of active parameters is also half. So instead of 13 billion active parameters, we only have 6.6. What this means is, let's see. Yeah, basically with our new MOE training recipe, we can produce these models that are more efficient to train, right? Half the training flops, and simultaneously more efficient to serve. So half of the inference flops as well. And that's one of the key components of our improvements from last year's MP2 models. Cool, so now we're gonna get into a little bit more detailed training math. So you saw before, how the different components of data and model parameters go in and how we pick those ratios. But let's go now into actually training a model on a cluster. How many days is it gonna take? How much money is it gonna cost? And there's not too many resources out there, but you'll see from our blog post, you'll see an evolution and kind of how we've been thinking about this, but this will be a quick 5-minute overview. All right, so let's pretend that we want to train a kind of standard 7 billion parameter model. We will use a chinchilla amount of tokens, and we're training this with Databricks. We have H100s, and we're going to train on 64 H100s. How long is this actually going to take? Is it a day, a week, a month? Well, let's dig into the components. We want to figure out the amount of compute, which we call flops, basically floating point operations. And a very rough heuristic for this is 6 times parameters times tokens. It's surprising how well this approximation works, and it's actually pretty easy to do on your iPhone calculator at home. So anytime you read a paper and they mention how big their model is, you can very quickly tell 6 times model parameters times tokens. You can figure out, all right, how much compute was it? If you're a real hardware nerd, you can eventually start labeling models in terms of their flop counts. You might say, GPT-4, oh, that's a 1E25 model, or Llama 2, that's like a 1E23. Anyway, when we want to figure out how much time it's actually going to take, well, our GPUs have, in theory, a certain number of floating operations per second that they can crank through. When we're doing these transformer training steps, it is mostly matrix multiplies, and GPUs come with a data sheet that tells you how many floating point operations it can do when you do these matrix multiplies. So for A100s, yeah, all right, we're going to train on A100s instead, and it's going to be fine. H100s are faster. So with A100s, you get 312 teraflops per second, and that's what you have there. So we have our data, we have our flops, and yes. So we basically take, the total cluster, 64 times 312 teraflops. That tells us the total amount of flops per second, and then we just divide it out. So 6 times parameters times tokens divided by the cluster flops tells us, okay, 3.4 days. Not too bad. Actually, when you think about it, some of these models just a few years ago were basically like state of the art, in GPT-3, and nowadays we can do them in just about 3 days. But there's one key component here missing if you try to do this back of the envelope math, and that's the efficiency of our GPUs. So in practice, you don't actually get that full 300 teraflops per second. You don't actually even get close to it. In reality, you may often get somewhere between 40% to 60% of the theoretical flops, and we call this the model flop efficiency, or model flops utilization, or MFU. So let's see that. And the reason this happens is because it's a combination of the fact that the sizes that our model uses for its layers are not necessarily super duper wide. These GPUs are most tuned to do matrix multiplies of, say, 64,000 by 64,000 elements. And most of our models are not that big. Their actual layers may only be 4,000 by 4,000. So they're not actually going to achieve that peak flops that is advertised. There's also a lot of other layers in the models, such as the self-attention layer. You may have layer norms and things like that. And so all these things add up, and you don't actually get to that peak. So what we try to do is dial this all down into one number, the MFU, which is basically what fraction of that peak utilization am I going to get. And for us, when we train, I think this may be with dense models, we get around a little bit over 50% MFU. On different GPU types and stuff, it varies a little bit, but basically our job on the performance team is to make sure that we're constantly optimizing MFU for every hardware type and every model that our customers are training. So let's redo that math now again with the MFU calculations. So everything's the same, except we just have to make sure we divide the cluster flops. We have to account for the MFU, and now we'll see it'll actually take 6.7 days instead of 3.4. So MFU is a really big deal, especially as you're looking at these big pre-training runs. Every 10 or 20% MFU points you can gain maybe like thousands or hundreds of thousands of dollars in terms of the actual training cost. And you can take that budget and sink it back into either training a higher quality model, use more data, use a larger model. And that's why we're constantly pushing this MFU in terms of our software, in terms of the GPUs we choose, like actually even the clusters we choose and the interconnect that we have. So if you're ever thinking about training a model, make sure you ask your provider what MFU do you get. All right, so now taking a step away from the models, when it actually comes time to train these things, there are a lot of software tools that actually go into it, some of which are open source. During our time at Mosaic, as well as here at Databricks, there's many open source libraries that we've developed and we've given to the community. And let's dig into that. I'm just going to list them all out here for a second. So we have basically training libraries both for the actual model, as well as the data set, as well as the whole package that went into train DBRX. And the majority of our software that we use for training DBRX is open source. When you train with us, we have some more proprietary speedups and kernels to make it even faster, to boost your MFU. But these are the different components we have out there. So Composer is a PyTorch training library that's basically designed to be really easy to use with any type of model, whether it's a vision model, whether it's an LLM. If you heard about some of our other image models this week, all of those models were all trained with Composer. So it's not necessarily for just LLMs. As Jonathan mentioned, we try to keep all of our data sets in object store, and this lets us basically provide privacy. It makes it so the storage is very, very cheap. When we train on different clusters, we don't have to replicate the data in many places. And streaming is open source and very high performance. And again, we use that not only for our text-based data sets, but also image-based data sets. I think we're adding support for video data sets. It's really, really awesome. To package this all together, specifically for LLMs, we have a library that builds on top of Composer and streaming that basically makes it very easy to pre-train, fine-tune, and evaluate LLMs of any size. Whether you want to test a really small 1 billion parameter model all the way to a 100 billion parameter size DBRX, and that's called LLM Foundry. And finally, when it came to actually implementing a mixture of experts efficiently on GPUs, we basically worked together with a collaborator, Trevor Gale, who built a library and associated research paper called Megablocks. And we recently adopted that into the Databricks ecosystem so we can continue to maintain it. And so Megablocks makes it really easy to run basically mixture of expert model kernels on GPUs, A100s and H100s, and we're going to expand that to more GPUs in the future too. Yeah, so definitely check these out. These are all open source. Yeah, and here's some links too if anyone wants to take a picture of that. Okay, I'll pause for just a few more seconds. Okay. Now, there are also some other tools in the community that we use, ranging from, of course, Megablocks, like I mentioned, is originally external, but now we've adopted it. PyTorch as well. Basically, all of our training library is built on top of PyTorch, and we use a particular library called FSDP, which I'll go into soon. When it comes to inference, we actually experiment with a lot of different stacks, and we're even building our own as well. We use VLM, we use TensorRT from NVIDIA. And when it comes to evaluation and data set curation, we have a lot of great collaborators from the Eleuther AI harness, people who've been working on that, as well as our friends at the Allen Institute, who have been pre-training their own open source models as well. I think if you haven't heard of Olmo yet, you should definitely check that out. It's a new, totally open model, actually trained on AMD GPUs, and using some of our software as well. Now, let's actually talk about what goes into training a model like DBRX on a really big cluster. So The number one thing to realize is that as you actually want to improve model quality and go up, these scaling laws, the amount of compute that's required is exponential, right? Going from Llama 2 to Llama 3, going from MPT to DBRX, we're not talking about using 2x the compute of the last time. We're talking more about like 100x. And so you have two big challenges when you try to scale up compute in this way. The first challenge is that the model is too big, right? It does not fit on one GPU anymore. 100 billion parameters, there's no single GPU in the world that can actually hold that in terms of all the model state and optimizer state. And the second problem is that the amount of compute we need to throw at this, I think for DBRX, we had somewhere around 3 E24 flops. If you want to actually finish that training run in any reasonable amount of time, you can't train on one GPU or 100. You actually need more like 3,000 GPUs. And so we have these two problems to solve. One is that how to fit the model, and then how to actually distribute it across enough GPUs to finish in a reasonable amount of time. And we'll talk about how we solve both of those here. So let's talk about the model first. We clearly need to split this across multiple GPUs. And there's a couple different ways we can do that. I'm actually going to talk about a few ways that we didn't choose first, and then I'll get to the one that we actually picked in the end. The first solution is pipeline parallelism. And what this idea is that instead of putting the whole model on every GPU, we'll split up into layers. Most of our transformers may have like 80 layers. I think DBRX has 40. So we could put layer 0 on the first GPU, layer 1 on the next. And then we'll just, as we're training, we'll pass the activations from one to the next. Now this is kind of nice because the layers never have to move back and forth. They can split up when we've separated the layer weights. But it has challenges in terms of how we manage the memory and how actually we tune it as well. One of the biggest issues with pipeline parallelism is that each GPU is now doing a slightly different amount of work and may have slightly different layers as well. And so you have to balance all these things. You also face this problem where as you feed an input through the model, it will go all the way to the end and back. And even if you actually pipeline many in a row, you have a bubble basically at the end where after the last input goes through, there's no other work to be done. You have to wait for it to come all the way back, and this bubble ends up wasting time. So although pipeline parallelism has some benefits, especially the communication requirements, we didn't want to choose that because of the complexity introduced. So let's talk about another way to split up models on GPUs called tensor parallelism. What this says, instead of actually putting different layers on different GPUs, we'll keep all the layers on every GPU, but we'll chunk them up. So layer 0 will get chunked up into maybe 100 little pieces, and a little piece goes on every single GPU. And then all we have to do to make sure is that we aggregate the outputs. So after every input, it goes through all the GPUs, and we aggregate the outputs and basically sum across them all. There's different ways to do tensor parallelism, such as column parallel or row parallel layers. And this has a different benefit, which is that now we don't have to worry about different memory management on each GPU. There's no bubbles anymore. But the problem is that we have to basically rewrite our model implementation. And this ends up being basically a barrier to doing fast research, which is that if I have to keep rewriting my models to accept these different forms of parallelism every single time, it's going to slow down the team. Not everyone is an expert in 3D parallelism on GPUs. And so we really wanted a solution where people could write their models independently of how they're going to be distributed. That was going to basically let us iterate the fastest and then get to that final architecture we want. So let's go to the parallelism form we chose, which is the simplest one, which is data parallelism. And I think, this is actually quite a big build slide. Let me get through all this. What this is we're going to basically replicate the model on every single GPU and only change the data, right? And so what this means is that there's no difference between the GPUs, no difference in the memory usage on each one. And the only thing we have to do is after every batch of data is done, we're just going to average the basically gradients across the GPUs. So data parallelism is like the simplest way to scale out to hundreds of GPUs. There's no problem whatsoever, except we did forget about one thing, which is that, never mind, it's a build again. Yes, all right, here we go. The one thing we forgot is that the model doesn't fit on a single GPU, right? So how can we possibly do data parallelism if the model is too big to fit on a single GPU? And that's where we get to this technique called FSDP. You may also know it from a different name, Zero Redundancy Optimizer, but FSDP stands for Fully Sharded Data Parallel. So we're going to do the exact same work, the exact same logic as data parallelism, but we're going to figure out how to split up the model weights so we don't hit that limit where the model's too big to fit on a single GPU. So let me see. Yeah. So what we're going to do, we're going to split every single layer of that model. Here we have a 3-layer model. We're going to split it up, and then we're actually going to shard it across the GPUs. So what that means is, GPU 1 is not holding the entirety of layer 1. It's only holding 1/4 of it. And it's holding the very first 1/4 of it. And then the second fourth is held by GPU 2, and so on and so on. And what this means is that actually now your model does not have to fit on a single GPU. It only has to fit on the entire cluster. And if we're using a cluster of hundreds or thousands of GPUs, this is tremendously more memory than is required to hold even DBRX, and this works just fine. So you'll notice we're not throwing anything away. It's not like we threw away any little piece of any layer. It's just kind of distributed across the cluster. So then how are we actually gonna train with this? How are we going to produce like a forwards pass through this model if it's split up in this way? And we're gonna do something very silly. We're just going to gather the layers as they're needed and throw them away when they're no longer needed. So let's imagine now, again, we're feeding that input through all the different GPUs. All we have to do is right before layer one's needed, we'll tell all the GPUs, hey, let's pause right here, we'll have a barrier. Let's gather up layer one, share it with everyone, and now you can do the work of layer one, right? And then as soon as you don't need layer one anymore, we'll just toss it. We don't need it in memory anymore, and then we only need to gather layer two. So again, what's happening here is that the actual model weights only need to fit on the cluster, and even live during training, you only need to be able to hold at least one layer's worth during the actual training process. You don't have to hold all 3 layers, you just have to hold one of them at the time that it's needed. And this is what enables you to basically support any type of model with almost any parameter size as long as it fits on the cluster without worrying about all these different parallelism strategies. So FSDP is like the way we train basically all of our models today. Not sure what that is. But yeah, here's just like the whole build again of all, okay. sorry. I think when I was designing these, I forgot about the little build animations. But we use FSDP for this reason. It lets us basically separate the research work of determining what model architectures we want, what size of things we want from the actual like hardware performance, and we get to separate those cleanly. So we could have a performance team and a research team that don't necessarily need to be experts at both. We've been able to use FSDP to train diffusion models as well as LLM models. We'll be developing multimodal models in the future. And we're really excited so far with the performance we've seen. We've scaled this up to thousands of GPUs. We worked together with PyTorch to make this work. If you're also training models out there today and haven't tried FSDP before, definitely give it a try. And as I mentioned, if anyone is interested in learning more after the fact, you'll find some really nice write-ups both from the PyTorch team as well as the original authors who invented this technique. And back then it was called the Zero Redundancy Optimizer. And if you're not familiar with computer scientists and their habits for naming things, the abbreviation for Zero Redundancy Optimizer is in fact zero. So it ends up being an abbreviation containing itself. But yeah, easy to remember. All right. So at this point, we've gotten to the stage where we know the model architecture we want, we know like the distribution strategy for this, and then we're actually going to just train it. So you might think all we got to do is collect a couple thousand GPUs. We'll call up Jensen or someone, and then we have our beautiful software, and then we'll just hit enter, right? It'll just work perfectly, right? And that is not at all what happens. We have, I think, in our time at Mosaic, been through like a couple different stages of training evolution. I would say when we went from one GPU to multiple GPUs, that was one big step. When we went to one node, where each node has about 8 to several nodes, that was another big step. And then I would say since like our MPT days or so, we've been at the stage where we can comfortably train on, say, up to 500 GPUs. And we thought, well, that's pretty good. If we can train on 500, surely we can do 1,000. Surely we can do 2,000 or 3,000. What could possibly break between those stages? And it turns out a lot does. And you won't even know until you get there. And that's why it's really important that we kind of take the first step ourselves, right? So we do DBRX as a way to basically battle test the stack and ensure that we can actually like support models at that scale before any customer ever has to. And so that's kind of like what the benefit of our product is. So let's talk about some of the things that break. The first is training instability and loss spikes. So how many people have ever seen a curve like this before? Yeah, I have some friends who I know have seen a curve like this before as well. So yes, so what this is that when you're actually training your models, you have a loss function and you want it to go down as close as possible to 0. You have these really scary effects where many iterations into training, maybe halfway through your training run, you'll get this spike where suddenly everything will derail. And these can be really scary, especially if you have a really big hero run or pre-training run on the line and you spent hundreds of thousands of dollars here. So what we've had to do over time is basically develop strategies for avoiding the loss spikes, and in the early days, also strategies for how to roll back and correct these when they occur. What we've developed over time since MPT through DBRX is basically special hyperparameters and recipes that mitigate these loss spikes. We have little architectural tweaks that prevent these from happening, as well as we know how to change our optimizer so that these don't occur either. And so in the earliest MPT days, we had a lot of these rollback strategies that were required, and using our streaming data set made it really easy to roll back deterministically. But we've actually tuned it to such a degree now that with DBRX, we don't even counter these loss spikes at all anymore. So that's one of the benefits of using our stack. So training instability is one thing, but the really, really painful part with training at these scales is the hardware failures. So this may come as a shock to people who have worked CPU clusters before and not necessarily GPUs, but GPUs fail really often. And it's not necessarily like direct hardware failures. It sometimes is just like issues with the communication libraries or memory correction errors. The problem is that these devices are running really hot 24/7 and they have a ton of memory interfaces on them. And when you're training on thousands of them, something is bound to fail. What we find within the runs that we do is that roughly once every 1,000 GPU days, so what that means is if you have one GPU once every 1,000 days, or if you have 1,000 GPUs, then once a day, we'll encounter some kind of failure. And this basically brings down your whole training run. And the problem is exacerbated by this fact that all of our training runs use synchronous training, right? If we train on 3,000 GPUs, if even one of them fails, then the whole thing goes down. It's not like we can isolate and throw it out. We are looking into strategies to try and do better than that, but that's the state of affairs today. So instead of like this thing where 1 out of n things can go wrong, you have this like kind of n squared problem where if every single switch between every single GPU is a failure point, that's you encounter. So if you do the math here with DBRX, we're reaching on 3,000 H100s. We basically had a failure every 8 hours. So every 8 hours, the run was crashing. What that means is that we have to have really resilient checkpointing. We have to have really resilient restarts. We have to make sure this is automated. We have to make sure that people aren't being woken up at like 3 a.m. in the middle of the night. And surely we had this set up before, right? No. Yes. So and again, I'll replay the history here. We'd been training MPT-sized models and so on for almost a year. We'd been doing lots of runs at 500 GPU scale, and everything was fine. We had lots of automated, error correction. We had lots of ways of restarting the runs. But this wasn't sufficient to make it to that 3,000 GPU scale. And we have specific channels where we would automatically catch every single failure that came in. We had basically on-calls around the clock on the research team. I would say January to March was a very traumatic time for the Databricks Mosaic team. But we went through all of that trauma so that we could actually build these automated detection systems. We found, basically, we cataloged every single nickel error or like hardware error that we found. And we basically figured out a way to detect these automatically, make sure we have spare GPUs, be able to restart the run really, really fast, and also be able to checkpoint really, really fast so that the amount of time lost on every restart was not slowing this down. Again, this is where the math becomes really important. When we have failures almost every like 8 hours, or let's say like even 5 or 6 hours, you really want to make sure that your time lost is no more than 20 or 30 minutes, because otherwise, 30 minutes every 6 hours, that's a pretty significant chunk of your training time just being lost to restarts, and that actually happens at this scale. So yes, so nowadays if you're a customer, you will not see any of these problems. We have automatic failure detection and restarts, and this is basically what it'll look like after. So these are some, I think on the right is actually a real customer channel we had where they were doing a hero run, and sometime in the middle of the night, I think maybe like 1 a.m. or something, they had a failure, and they woke up the next morning and, oh, I didn't even know it happened. And that's kind of the outcome that we want to see for all of our customers. So yes, what else we have? Oh, I think that's actually pretty much coming to the close of like the actual talk portion. I think we'll do some questions as well. And I'll definitely want to invite Jonathan back up on stage for that. But I just want to repeat the friendly advice we talked at the beginning, right? So even if you want to train a DBRX size training run, and we will be very happy to help you do that, we do recommend you start small and work your way up. Start by trying out the open source foundation model. Start even by trying out ChatGPT. Figure out what your evaluation sets are, and then figure out like what quality and also what latency, what speed you need. Don't trust necessarily everything you see in the literature. Don't trust what you see on Twitter. Make sure to try things out for yourself, or consult experts who have maybe like tried a lot of things out. Test everything for yourself. Don't necessarily trust your intuition either. I myself have had lots of debates with team members about like, oh, I'm sure this idea will work. It seems so elegant. It seems so nice. And then you actually try to run like a series of scaling law experiments, and it doesn't scale the way you think. So make sure that you have a setup that makes it very easy to experiment and try out new things rapidly, right? So that's part of the reason why we wanted that distribution strategy that was so simple. It lets us try out ideas in say days instead of months. And finally, do the math, right? A lot of the math we talked about today is basically just multiplication. A lot of these kind of numbers, these constant factors, you can look up in data sheets. And I think usually all it takes is one Google sheet where you can basically figure out parameters, tokens, what the cost is going to be. We have a lot of these kinds of tools internally, but it's actually pretty easy to figure out what would it take for me to train a DBRX-sized model or a Llama 3 model, or even approximating up to GPT-4. You can do the math yourself. Of course, we're there to help you as well. So if you want to basically use the best recipes and get the best optimizations out of the box, come work with us at Databricks. We will be very, very happy to show you battle-tested recipes and software that will allow you to train your own models, and we can help you too. We're really good at all these different components, and we've done it before. That's basically the message here. So thank you all again so much.